a quantity called the divergence. So let me write this. We defined a quantity called divergence that told us about whether in an enclosed volume there was a net outflow of the vector field or net inflow of the vector field, and therefore it was related to source or sink of the field. We are now going to specialize to electric field and talk about the divergence of an electric field. Recall that electric field is a vector quantity which is a function of x, y, and z. I can also write this as a function of vector r. So its divergence is going to be the sum of the partial derivative of x component with respect to x, partial derivative of y component with respect to y, and partial derivative of z component with respect to z. And again, recalling how we defined it, if I take a closed volume and take over all these surfaces, taking the area vector to be pointing away or pointing out of the volume, if I take the sum of E field on each surface, dot it with the area, and sum over the entire all the surfaces, what this means is I am taking the component along the direction or perpendicular to the area and multiplying by the area. This was equal to the small volume, let's call it delta V, times the divergence. And this is what told us about how it works, as a divergence indicates what a source or a sink is. Recall that if this quantity is 0, there is no divergence, and therefore a field or some integration of the field over the area has to be non-zero in order for divergence to be non-zero. And this, in the case of electric field, is defined as the flux. So let us now calculate the divergence of the electric field due to a charge. Electric field E at a point x, y, z is given as integration rho r prime over r minus r prime cubed. I am deliberately writing it like this so that you get used to it, dv prime, that is I am integrating over this primed volume, 1 over 4 pi epsilon 0. To start with, let us write the electric field for a point charge, which is at x, y, z, it will be given as 1 over 4 pi epsilon 0 q r minus r prime over r minus r prime cubed, where the position of the point charge is at r prime, and I am calculating electric field at r, this vector being r minus r prime. And let us take its divergence. Before that, let me write the individual components of the electric field. Ex, x, y, z is going to be 1 over 4 pi epsilon 0 x minus x prime divided by, let us open this whole thing also, is going to be x minus x prime square plus y minus y prime square plus z minus z prime square raised to 3 by 2. Similarly, Ey at point x, y, z is going to be equal to 1 over 4 pi epsilon 0, or there has to be a q here, which I made a mistake, q, y minus y prime over this whole thing, x minus x prime square plus y minus y prime square plus z minus z prime square raised to 3 by 2. And quickly I will write the z component also. E z at x, y, z is going to be 1 over 4 pi epsilon 0 q z minus z prime over x minus x prime square plus y minus y prime square plus z minus z prime square raised to 3 by 2. Let us now calculate partial of Ex with respect to x. Notice that this is Ex is a function of x, y, z, so I am taking partial derivative with respect to x, which is partial derivative of 1 over 4 pi epsilon 0 q x minus x prime over x minus x prime square plus y minus y prime square plus z minus z prime square raised to 3 by 2. And you quickly do it, this comes out to be q over 4 pi epsilon 0 is common. First term gives you 1 over, let me again for the lack of space write this as r minus r prime cubed plus x minus x prime. Now I am taking partial derivative of this 1 over r minus r cubed. So this will give you times minus 3 by 2 1 over x minus x prime square plus y minus y prime square plus z minus z prime square raised to 5 by 2, and on top I will get 2 times x minus x prime. So this comes out to be q over 4 pi epsilon 0 1 over r minus r prime cubed minus 3 x minus x prime square divided by r minus r prime raised to 5. I can similarly calculate partial Ey over partial y, and this will come out to be q over 4 pi epsilon 0. You can check this, 1 over r minus r prime cubed minus 3 y minus y prime square over r minus r prime raised to 5. And partial E z over partial z comes out to be q over 4 pi epsilon 0 1 over r minus r prime cubed minus 3 z minus z prime square over r minus r prime raised to 5. In all this, we have taken r vector is not equal to r prime vector, because then this term will vanish and whatever mathematics I am doing will not be valid. If I add all this, so this condition you should remember. If I add all this, what am I going to get? I am going to get partial x over partial x plus partial Ey over partial y plus partial Ez over partial z, which is nothing but divergence of E x, y, z is equal to, these terms together give me 3 over r minus r prime cubed. So I get q over 4 pi epsilon 0 3 over r minus r prime cubed minus 3 x minus x prime square plus y minus y prime square plus z minus z prime square gives me modulus r minus r prime square divided by r minus r prime raised to 5, and this is 0. So as long as you are not sitting on the charge, the divergence of the field is 0. So what we have learned is, if I take a point charge q at position r prime and calculate divergence of E at some point r, this is 0 for r not equal to r prime. So now if I take a charge distribution, as long as I am away from the charge distribution, that means at a point at a point where there is no charge. Divergence of electrostatic field will always be 0. What it means is that integration E over a volume where there is no charge is 0 over a volume that encloses no charge. But what about a volume that encloses a charge? Let us now look at that. Suppose I have a charge Q at r prime, and I make a volume, spherical volume, because that is easiest to handle, around it. So let us look at this charge and the volume around it. Then I know field lines are going to go out like this everywhere. And area, as we already discussed, also points away from the volume perpendicular to the surface. I'll talk about this perpendicularity and all that a little more later, but right now just take that ds, we are going to take, the area is going to be taken at every point pointing away from the surface, pointing out of the volume on the surface perpendicular to the surface. So you see E and the surface are parallel everywhere, and therefore E dot ds is nothing but E times the area there. Now I know for a point charge E is Q over 4 pi epsilon 0 1 over r square, where r is the distance from the center. So its value of E all over the surface, all over the spherical surface is the same, and therefore if I take E dot ds is going to be 4 pi r square Q over 4 pi epsilon 0 1 over r square. This cancels, 4 pi cancels, and this comes out to be Q over epsilon 0. So now I know for a point charge E dot ds around it over a sphere is equal to Q over epsilon 0. Is it true for any surface? Let us see that. If I make an arbitrary surface, then E dot ds over the volume between two surfaces is going to be 0. Why? As we have already seen that E dot ds integral is divergence of E dV, and there is no charge in this region in between. If there is no charge in between, then this is going to be 0. If this is 0, that means whatever flux is coming in, whatever electric field lines or flux is coming in, same flux is going out, because there is divergence in between is 0. And this implies that E dot ds over any surface is Q enclosed by that surface divided by epsilon 0. That surface need not be spherical. Okay, so let us bring all this together, whatever we have learnt, and write the general expression for the divergence of an electrostatic field. So, let us see what we have learned. If I am given a charge distribution, let me call it rho of r, what we have learned, number one, that divergence of E is equal to 0 for points outside the charge distribution. Point number two that we have learnt is that if I write the flux of the electric field, or what we now write E dot ds over a surface, this by divergence theorem is equal to divergence of E integrated over the volume surrounded or enclosed by the surface. And third, that if I take E dot ds over a surface enclosing a point charge, this is equal to that point charge amount divided by epsilon 0. And it does not matter where the surface is, the point charge, as long as it is enclosed by some surface. I am making 2 or 3 surfaces just to emphasize that surface could be of any shape, spherical or non-spherical, elliptical, or any arbitrary shape. So, I'll use these 3 facts now to show what the divergence of electric field is. So, let us take this charge distribution rho r inside the surface and consider a very small volume, could be spherical or any shape inside it. Then at any point inside the surface, I can write electric field E as E1 plus E2, where E1 is equal to field due to charges inside the volume, and if the volume is small enough, we can think as if the field is roughly the same at all point, and E2 is equal to field due to charges outside the volume. And then by whatever we have learnt, divergence of E is going to be equal to divergence of E1 plus divergence of E2. However, divergence of E2 is 0 because E2 is due to charges which are outside this volume. So, this is 0, and therefore, this is divergence of E1. So, if I now write the volume integral divergence of E at a point integrated over the volume, this is equal to divergence of E1, where E1 is the field due to charges surrounded by this surface, is divergence of E dot dV, which I can write as E1 dot ds over the surface, and this is nothing but equal to charge enclosed by epsilon 0 in this volume, which we just saw just a few minutes ago. Charge enclosed for a very small volume I can write as the charge density inside times the volume delta V. And on the left hand side, again, if the volume is small enough, divergence of E can be taken to be the same over the entire volume times delta V. And now you see delta V cancels on both sides, and I get divergence of E inside this charge distribution is rho over epsilon 0. there is an epsilon 0 also out here. And therefore, I can write now that Q dot E at any point is equal to rho at that point, or the charge density at that point, divided by epsilon 0. If the charge density is 0, that means I am outside the charge distribution, divergence is 0, and if I am inside the charge distribution, divergence is that density divided by epsilon 0. So, this is the most general statement for the divergence, and this is known as the differential. Is known as the differential form of Gauss's.